At the top of a loop, nothing is holding you in your seat. Not the harness, not friction. Just speed and the people who calculated exactly how much you need. To understand the scale, think about a modern steel coaster, like King Ka at Six Flags Great Adventure. It stands 139 meters tall and accelerates from 0 to 206 kilometers per hour in just 3.5 seconds. The entire train, loaded with passengers, weighs several thousand kilograms, and it does all of this without an onboard engine. No combustion, no propeller shaft, nothing mechanical turning inside the cars themselves. By common sense, something that heavy moving that fast should require enormous machinery. But physics says otherwise. And everything you see on a modern roller coaster is the result of over a century of engineering, failed prototypes, and relentless refinement. The origins go back further than most people expect. The concept traces to the 16th century Russia, where wooden ramps covered in packed ice sent riders down 70-foot slopes on sleds. It wasn't a thrill ride in the modern sense. It was winter entertainment, but the principle was already there. Use height. Let gravity do the work. In 1884, LaMarcus Thompson opened the Gravity Switchback Railway at Coney Island. It reached a top speed of around 10 kilometers per hour. Crowds lined up anyway. Something about controlled falling turned out to be deeply compelling. After that, progress accelerated. Steel replaced wood. Loops replaced simple hills. Computer-aided design replaced hand-drawn blueprints. And somewhere along the way, engineers stopped relying only on gravity and started building machines that could throw a train to top speed in seconds using nothing but magnetic force. But despite all the innovation, the core principle never changed. A roller coaster is always about energy, where it comes from, where it goes, and how precisely you can manage it. So how does a machine with no engine actually move? The answer lies in two fundamental concepts that govern every roller coaster ever built. The first is potential energy. When a chain lift pulls the train to the top of the first hill, it's not just moving the car upward. It's storing energy in the form of height. The higher the train climbs, the greater its potential energy. Think of it like pulling back a slingshot. Nothing is moving yet, but the capacity for motion is being loaded into the system. That slow, clicking climb isn't just building anticipation. It's building the only fuel the ride will ever have. The second is kinetic energy. The moment the train crests that first hill and gravity takes over, potential energy converts to kinetic energy, the energy of motion. Speed increases, the train accelerates. And as long as the track continues to drop, the conversion continues. Every meter of descent translates directly into speed. The steeper the drop, the faster that conversion happens. That's why the first hill on a coaster always feels the fastest. It is. But here's what most people don't think about. That first hill is the highest point of the entire ride. Every hill, every loop, every element that follows must be shorter than the one before. Not for dramatic effect, because of physics. Energy is lost to friction and air resistance on every meter of track. The train cannot climb higher than the energy it has. If an engineer miscalculates and designs a second hill taller than the first, the train simply stalls. It doesn't make it over. That's why roller coaster layouts are not arbitrary. They are precise calculations of energy available versus energy required at every single point on the track. Every curve, every twist, every moment of the ride has been run through simulation before a single piece of steel was ever ordered. One of the most misunderstood elements of a roller coaster is the loop. Most people assume it works like a barrel roll. That centrifugal force pins you to the seat and keeps you from falling. That explanation is incomplete. What's actually happening is more elegant. At the top of a loop, the train is moving fast enough that centripetal acceleration, the inward acceleration, required to follow a curved path, exceeds the pull of gravity. The track doesn't need to push you up. Gravity and the track together provide exactly the force needed to keep the car on its circular path. The result is that riders feel compressed into their seats at the bottom of the loop and light, almost weightless, at the top. That sensation is not an accident. It's designed. And here's something most riders never notice. Modern loops are not perfectly circular. Early circular loops in the 19th century caused serious neck injuries because the G-forces at the bottom were too extreme. Engineers eventually solved this by using a teardrop shape, wider at the bottom and narrower at the top. This geometry naturally reduces speed at the top and distributes G-forces more evenly throughout the entire element. The shape of the loop is not aesthetic. It is a direct response to what the human body can and cannot tolerate. This is where G-force becomes critical. G-force is the measure of acceleration felt by the human body relative to normal gravity. At rest, you feel 1 G. At the bottom of a steep drop, you might feel 4 or 5 G. Your body feels 4 to 5 times its normal weight. At the top of a loop, you might feel close to 0 G, the sensation of weightlessness. The human body can tolerate approximately 5 G for short periods without harm. Engineers design every element of a modern coaster to stay within those limits. Not because the structure can't handle more, because the passengers can't. Negative G-force is equally important. When a coaster crests a hill faster than freefall, riders experience airtime, a moment where the body lifts against the harness and feels genuinely weightless. Coaster designers treat airtime as a feature. They calculate exactly how much negative G each hill will produce and place those hills deliberately in the layout. That floating sensation over a camelback hill is not luck. It is the result of a specific speed, a specific radius of curvature, and a specific angle, all calculated in advance. But what happens when a roller coaster doesn't use a lift hill at all? That's where modern launch systems enter the picture. And this is where a common misconception needs to be cleared up right away. Launch coasters do not use engines inside the cars. There is no combustion. Instead, they use electromagnets embedded in the track itself. The two most common systems are the linear induction motor, or LIM, and the linear synchronous motor, or LSM. Both use rapidly alternating electromagnetic fields to accelerate the train without any physical contact between the track and the car. With an LSM system, permanent rare earth magnets are mounted to the underside of the train. As the car approaches each set of powered stators on the track, the magnetic field attracts the train forward. As the train passes over each stator, the polarity reverses and repels the car forward again. This sequence fires dozens of times per second, controlled by computers, producing a smooth and continuous acceleration. Formula Rossa in Abu Dhabi, using a hydraulic variant of this principle, reaches 240 kilometers per hour in 4 seconds. That's faster than a Formula One car off the line. The stopping process is no less precise. Magnetic braking systems use the same electromagnetic principle in reverse. Permanent magnets on the train pass over aluminum fins on the track. The interaction generates eddy currents that oppose motion and slow the train down with no physical friction, no brake pads, no wear. The braking force is proportional to speed. The faster the train enters the brake run, the stronger the force applied. The result is a deceleration that adjusts automatically and brings the train to a controlled stop every single time. No mechanical contact, no components wearing down. Just physics, doing exactly what it was told. So, what actually happens during a launch sequence? Before the train even leaves the station, computers calculate the precise timing of every magnetic stator along the launch track. The moment the system is armed, the sequence fires. Magnetic pulses travel down the track in a wave, timed exactly to the position of the train. Riders feel not a jerk, but a smooth and escalating push, as if the track itself is breathing force into the cars. Within seconds, the train has more kinetic energy than a chain lift could have provided in a full minute of climbing. After the launch, the ride becomes a closed energy system, exactly as it was in 1884. Height converts to speed. Speed converts back to height. Every hill, every inversion, every banked curve is a precisely engineered exchange of energy forms. Engineers run computer simulations of the entire ride before a single piece of steel is manufactured, calculating forces at every point, checking that G-loads remain within human tolerances, ensuring that energy is sufficient to complete the circuit with a safety margin at the end. There is one final detail that most people never consider. The train that returns to the station always arrives with slightly less energy than it left with. Friction took some. Air resistance took some. That deficit is intentional. If the train arrived back with the same energy it started with, the brakes would have nothing to do. Engineers designed that energy loss into the layout on purpose, managing exactly how much the ride consumes so that every return is predictable, controllable, and safe. Every time you watch a roller coaster launch, it looks like pure chaos. Screaming passengers, roaring speed, steel bending into impossible shapes. But it's not chaos at all. It's a system in balance. Potential energy, kinetic energy, magnetic force, G-force management. Everything exists in precise sequence. To me, that's what makes roller coasters extraordinary. Not the drops, not the loops. The fact that every single one of those sensations was calculated in advance, down to the fraction of a second.